All right, moving into constant speed propellers. Okay. You've been flying them at Western, been flying them in the Cirrus, whether you realize it or not, you are flying constant speed propeller. Let's take a peek at some of the forces involved in the propeller. Let's get our orientation here first. First of all, you see the gray shape up here, and that is the airfoil shape. So that's the propeller blade. Three-dimensionally, this propeller blade would be coming out of the screen towards you. And because we have a leading edge right here, it would also be moving downwards towards the floor as it rotates. Because we have a leading edge, we also have a trailing edge of the airfoil section. We can draw a chord line between those two reference points. Axis of rotation, just think of that as the propeller shaft coming off the engine. Rotating downward. So the perspective of the propeller blade as it rotates is there is an induced airflow coming up toward the blade. So imagine yourself like you're a fly on the propeller blade. Your perspective is, I'm not moving, the world is, and I'm feeling an airflow coming at me. Because that propeller has that blade angle to it, it's also pulling in an airflow to it. It's an induced airflow. I think I got to back up for a second here. I misspoke. This little vector right here is a rotational airflow. And this black vector here is the induced airflow. And you felt that airflow when you are behind an airplane and you got blasted from the prop wash. That's the induced airflow. Once the airplane begins moving, there's more air coming in from the speed that you're at. So we got our horizontal vectors, our vertical vectors, components there. We can make one resultant force here. Okay. That resultant force, I can give it another name to help you understand a little bit better. We would call it relative wind. Let's face it, we're dealing with an airfoil. And with an airfoil, you have a relative wind. The angle between that relative wind and the chord line becomes your angle of attack. So we take a peek here at blade angle. Currently, our angle of attack here is very shallow. So we would call this fine pitch or shallow blade angle. It's a small angle of attack. So you'll hear those terms kind of used interchangeably here. Oops, sorry, I hit the play button too soon. When we want the blade to go to a steeper angle of attack, right? This is what it pretty much looks like. Right? We can now see that the angle between that resultant vector or that relative wind vector here and the chord line makes for a much greater angle of attack. And that is what we would call coarse pitch. It's a large angle of attack. Okay. Again, those are some terms you probably hear interchangeably there. So that's the whole point of your blade angle, is for it to kind of adjust this angle of attack here throughout various phases of the flight. Of course, if you get into the Seminole aircraft, it has the capability to feather, and this is what a feather condition would look like. Propeller blade right into the airflow. So let's try a top hat question here. First. Let me go back to this real quick here and just talk about it. quick moment. You need to think about blade angle, kind of like the gears on a bike. So if you've ridden a mountain bike, you have different gears that you can switch to, and you know that some of those gears are real easy to pedal through, and some gears are really, well, they take a lot of effort to pedal through them, right? So imagine you're on your bike here, and you're just starting out. You want to be kind of in those smaller gear ratios, right? Because it's easy for you to pedal. That's real easy, okay? And you can start to build up some speed. And if you want to go faster, you start pedaling faster. But you get to that point where, well, I'm pedaling so fast now, I'm not getting any faster, but I'm working too hard here, right? So you switch gears. Right? So you switch gears and you make it a little larger of a gear sprocket, or make it a little bit larger of an angle of attack. And you notice, okay, I don't have to pedal as fast, but now I'm putting a little bit more effort into my pedaling, right? And if I want to go faster, I just start pedaling faster again. And it gets to the point where I'm just pedaling so fast, I'm not getting any faster, but I'm working really hard. So you shift gears to a larger gear. Or in the airplane, we would go to a larger angle of attack. And you would keep that process going so that the faster you got to help maintain the most efficient blade angle, the blade angle would be adjusting itself on that. So our question on top hat relates to the propeller position that represents takeoff. Okay? Now this is a touch type of question, all right? So just like the gears on a bike, right? You want small gear when you are getting started. This is takeoff, we're just getting started. See if you can figure out the question here. All right, so just like our bike example, we're starting off slow. We need to have that shallow, or that small gear, we need that shallow blade angle. Okay. So the one on the right, between the resultant force, or that relative wind force, and the chord line, that's the shallow distance there. So that represents the takeoff position of the blade. The one on the left represents a more of a cruise situation where you're at a fast speed. We're trying to make the blade as proficient as possible. Try another one here. Which one is set for a coarse pitch? Do you understand the term coarse pitch? All right, most of you did get that one correct. So the one on the left is the coarse pitch. That's what we would want in cruise flight. Higher blade angle. The one on the right is a fine pitch, small blade angle. That's what we use for takeoff there. So how does the blade do it? How does it move? There's definitely some forces up inside that propeller spinner. And we're also adding another force to it from oil pressure. So the propeller governor's got some main parts. There's 5 parts that we're going to talk about in the system, and 4 of them make up the governor itself. We'll talk about each of these individually. We'll talk about the prop controller, the speeder spring, pilot valve, and the flyweights. So it is important that you understand how these operate. We would expect at the commercial pilot level that you know how these parts work, which way oil flows in the system you're describing. So let's start with the prop controller. And I'm going to show you the control system that you would see in most typical airplanes with a constant speed propeller system. Now your Cirrus combines the prop controller and the throttle into one single lever. Nice bit of engineering there, but most aircraft are going to have that blue knob over here for the propeller controller. So the thing to remember with the propeller controller is when you push that forward, you want more RPMs. Very similar with throttle. When you push the throttle forward, you want more power, right? So blue knob forward is going to be more RPMs out of the engine. So that means there is an actual cable running from your cockpit to the governor. And when you get a chance to go down to maintenance, see an uncovered engine, you can look for that connection in there. Doesn't matter if it's the Cirrus or the Seminole, you'll be able to find that. Now here's the thing, that forward movement of the knob puts more pressure on a spring. Okay? And that's our next one to look at, the speeder spring. So there would be a little connection here. Very crudely drawn prop handle. And it's in the cockpit there, that blue handle. And it's connected to a plate right on top of the speeder spring. And by pushing forward on the prop controller, you are compressing the speeder spring. So you're trying to sandwich it closer together. Of course, that speeder spring is resting on top of flyweights. 2 on either side there. So now we have a downward force on the bottom of those flyweights. Flyweights are pivoted about this connection point right here. So the speeder spring is providing that downward force on it. You can always make your own speeder spring by taking your thumb and index finger and holding them up. And the pivot point is where the right angle here for your finger and thumb kind of meet. So you can imagine the speeder spring's resting on your thumb, pushing downward on it. And if you push downward on your thumb, it just naturally wants to rotate the top of the flyweight inside. Now the flyweights are connected to this critter called the pilot valve. We'll talk about that in a moment. But let's talk about these flyweights because they spin at about the same RPM of the engine, or they're proportional to it. So as the RPMs of the engine change the speed, there's a different force acting, centrifugal force acting outward on those flyweights. So now we got 2 forces involved here. And again, we got that pivot point on both sides there. So your speeder spring was pushing down on your thumb, but centrifugal force is pushing outward on your top of your finger. So what really comes into play here is how are those 2 forces balanced with each other? If they're equal, that means something. If one's greater than the other, that also means a couple of different things. Let's look at that pilot valve for a moment here. because it's a valve. And valves control the flow of something. In this case, it's the oil flow. It either allows oil into the spinner to move the blade angle one way, or it allows oil to come out of the spinner to allow the blade angle to move the other way. We are using system oil. And your governor does have its own little gear pump in it to help boost that pressure up. Again, pilot valve is just controlling the flow of oil into and out of the spinner. So let's take a top hat question here. The pilot pulls on the blue propeller knob in the cockpit. The pilot wants to what? So when the pilot pulls on the blue propeller knob in the cockpit, we've been talking about pushing. Now the question is on pulling it. Oh, you're out quick today. Good. All right, reduce RPMs. There we go. That is correct. Reduce RPMs. If we're talking about prop controller, we're talking about RPMs. We're not talking about manifold pressure. Another question. When the pilot pulls on the blue propeller in the cockpit, so the blue propeller knob, what happens to the pressure on the speeder spring? It's connected to a plate on top of that speeder spring. We're pulling the knob. Yeah, most of you got that right. So always remember, if we're pushing the blue prop controller forward, that's more. We want more RPM. So we're pulling it this time. That's a reduction. Another question. The pilot pulls on the blue propeller knob in the cockpit. Pressure in the speeder spring reduces, and the pressure on the bottom of the flyweights. Remember, you got flyweights, you got centrifugal force acting on the top finger, speeder spring pressure acts on the bottom. Remember that prop controller's making a sandwich out of that speeder spring. You're smushing the sandwich or letting off the pressure on it. Yeah, most of you got that one correct. So that speeder spring is affected by the prop controller. It's a sandwich effect. So pushing forward smushes your sandwich down, so to speak. And if you pull back on the prop controller, we are elongating the spring, so there's less pressure on it. Okay, last question here. When the pilot pulls on the blue propeller knob in the cockpit, pressure on the speeder spring reduces. Pressure on the bottom of the flyweights also reduces. Since centrifugal force remains the same, the top of the flyweights will do what? Remember they're hinged. If both forces were equal to begin with, And now we just reduced the bottom one. What's going to happen to the top of the flyweight? All right, most of you got that one right. Move outward. Okay. Equal forces on the two, right? If you remove the force on the bottom, that means centrifugal is greater. It's going to be moving the top of the flyweight outward. This is what it tends to look like here. So three conditions. Here we have an on-speed condition. That's going to be equal pressure, flyweights, speed of spring and centrifugal force. Middle one is an overspeed condition. So centrifugal force is greater. And the one on the right, probably guessed it, is an underspeed condition. So when we say on speed, we mean engine RPM is at the desired setting. And overspeed means RPMs are greater than what the setting was set by the pilot. So for example, if the pilot was setting 2,300 RPMs, the moment we go over 2,300 RPMs, we are over speed condition. And this system goes to work. Same thing if we set 2,300 RPMs, but the RPMs go below 2,300, that's the underspeed condition. So we take a look, overspeed condition. Our centrifugal force is much greater than the pressure from the speeder spring. That's causing the overspeed condition. It's going to cause the blade angle to increase. So oil is, okay, and let me just make a quick note here. This is a single engine constant speed propeller system, not a twin, right? We're going to be sending oil into the propeller hub to make the blade angle greater, more coarse. Now, what does that do? Aerodynamically speaking, when you increase this blade angle here, you are increasing what we call torque. Another way for you to understand that, we're increasing propeller drag. And if you increase the propeller drag and torque, you're going to cause it to slow down. So we're using torque to help regulate the speed of the propeller blade. So when the propeller blade spins too fast, overspeed condition, we get oil pumped right into it, greater angle of attack, more torque, we slow down. Okay, let's try a question here. So if the flyweights move outward, indicating an overspeed, then the governor system will move the propeller blade to which setting? Okay, so click on the figure. All right, most of you got that one. It is the one on the left side. Overspeed condition, we need a greater blade angle, more propeller torque to slow down the propeller. Okay. If the flyweights move inward, okay, that's kind of the opposite now, right? Inward's talking about not enough centrifugal force. Inward's your under speed condition. The governor system will move the propeller blade to which setting? So a propeller is not spinning fast enough. We need to reduce propeller torque or propeller drag to speed it up. Hey, y'all got it. Nice job. Looks like one person went outside the correct answer area. Sorry. But that is correct on the right side. All right, so just a quick little video here on propeller overspeed. We're recognizing speeder spring, flyweights, and the pilot valve here. So let's just play this real quick. Propeller goes into overspeed. More centrifugal force than spin pressure on the flyweights. They move outward. Pilot valve is now allowing oil to come into the system and make that blade angle greater. So up here is a little piston inside that spinner, and that piston is connected to that blade angle, and that's what's moving. More oil goes into that, moves that piston to a much greater blade angle. Now what happens? We start slowing down the propeller, and we go back to the on-speed condition, but notice that the blade angle remains the same now. Your propeller is constantly doing this every moment that it's spinning. And it just happens faster than I could snap my fingers. That's just how quick it is. On some days when you have the sun hitting the back of the propeller blade, you can actually see it move. Right? It's doing its job. So we're under speed condition, and we're going to the shallower angle of attack there. So let me just skip ahead to the video here and show you what's happening. Speeder spring comes in to an underspeed condition that moves inward. Okay? And now oil is allowed to flow out of the system. Shallower blade angle occurs. So what's up inside here? There is a couple different things happening, 4 to be specific. First of all, you have a spring in there that helps move that blade angle. Okay? That's one of your forces there. Second force up there is going to be counterweights. It'll be placed so that we naturally go to the low blade angle position. A third force in there is called asymmetric twisting moment. So it's helping the propeller blade go to the low blade angle as well. And then the fourth one is there's probably a air charge or nitrogen charge assisting the spring in there. Probably going to get the opportunity to see Mr. Langworthy step on this return spring. Right? He's got one from the Seminole. He can't budge it by standing on it. That's how strong it is. Plus you got the counterweights, asymmetric twisting moment, and the air charge up in there, all acting one way. The only thing that opposes that is the oil pressure the other way. So when the pilot valve opens up, all of these forces, the spring, the charge, counterweights, ATM, they push that piston the opposite direction, and the oil is forced out back into the reservoir. There we go. All right, so this is actually a good time to see if you got questions.